Hi, my name is Ashley Tyson, and this is Lab 2, Motion of a Falling Object. In this lab, we analyzed projectile motion using tracker video analysis and compared our experimental results to computational models. The person's experiment was to better understand how forces affect the motion of a falling object. This lab is based on Newton's second law, which states that the net force acting on an object equals mass times acceleration. In projectile motion, the main forces acting on the object are gravity and air resistance. Gravity acts downward and can be written as Fg equals mg. Air resistance or drag acts opposite the direction of motion and depends on velocity. In our model, drag was proportional to velocity squared. The total force on the object is the sum of gravity and drag, and we used free body diagrams to visualize how these forces interact during motion. For our setup, we used a paper ball as the projectile. The surroundings included the person throwing it and the air, which produces drag. We recorded this motion and used Tracker to analyze position, velocity, and acceleration over time. This allowed us to compare real experimental data to our theoretical predictions. Okay, here's a video. So for our observed motion, we see a curved trajectory that represents projectile motion. The vertical position changes non-linearly over time, which is consistent with constant downward acceleration due to gravity. The spacing between the points increases as the object falls, showing that velocity increases as it accelerates downward. In our first computational model, we ignored air resistance and assumed only gravity acted on the object. This produced a perfectly symmetrical parabolic motion. However, when we compare this model to our experimental data, we notice it did not perfectly match the real trajectory. When we included drag in the second computational model, the results align more closely with the observed data. The inclusion of air resistance changes how velocity evolves over time and slightly alters the position curve. From the velocity graphs, we can also see evidence of terminal velocity. In the gravity-only model, velocity increases linearly over time. However, in the drag model, velocity begins to level off, showing that drag eventually balances gravity. This demonstrates that the object approaches final velocity. Finally, when comparing a dropped object to a thrown object with initial velocity, we see that the initial conditions affect the motion early on. However, over time, gravity and drag dominate the motion, and both cases begin to show similar behavior. Overall, this lab demonstrates that including air resistance makes the computational model more realistic and provides a better representation of the actual motion of a falling object.